Imagine walking into a room where every sound feels crystal clear. No echo bouncing off the walls. No harsh noise fighting for your attention. Now imagine this. That calm, controlled sound comes from a product so complex that engineers spend years perfecting what most people barely notice. Every podcast studio, concert hall, office, cinema, and recording booth depends on acoustic panels. But here's what nobody tells you. Creating a panel that can tame sound waves traveling at over 1,200 kilometers per hour is far more difficult than building many mechanical products. Most people think acoustic panels are just pieces of foam attached to a wall. They couldn't be more wrong. Hidden inside these panels are carefully engineered materials designed to capture sound energy and convert it into tiny amounts of heat. The process involves minerals pulled from deep underground, fibers thinner than human hair, precision manufacturing lines stretching hundreds of meters, and testing chambers so quiet they can detect the sound of a single pin dropping. And what happens inside those factories might surprise even experienced engineers. Today, we're following a complete journey of acoustic panels from raw materials buried beneath the earth to finished products installed in world-famous bases. You'll see giant mining operations, massive fiber production furnaces reaching temperatures hotter than lava, automated cutting systems moving with incredible precision, and quality control tests that push every panel to its limits. But before any of that can happen, manufacturers need one ingredient that starts thousands of kilometers away from the final customer. Many premium acoustic panels begin with volcanic rock known as basalt. Large deposits come from countries, including China, India, Russia, Turkey, and parts of Northern Europe. Mining crews use massive drilling rigs and controlled blasting systems to break apart ancient rock formations that formed millions of years ago. A single manufacturing plant can consume hundreds of tons of basalt every day, transforming stone into one of the most effective sound-absorbing materials ever created. The rock leaves a mine in trucks, carrying loads that can exceed 40 tons each. Those trucks travel to crushing facilities where giant steel jaws break the basalt into smaller pieces. The sound is deafening. Steel crashes against stone while conveyor belts carry endless streams of crushed material toward processing plants. Most people never think about this stage, yet every acoustic panel depends on this violent beginning. Some manufacturers take a different path and use fiberglass as a core sound-absorbing material. Fiberglass starts with silica sand, limestone, soda ash, and recycled glass. High-purity silica sand often comes from specialized deposits in the United States, Australia, Egypt, and parts of Europe. Manufacturers carefully control purity levels because even small contaminants can affect fiber strength and acoustic performance later in production. Then comes a hidden sustainability story. Many modern acoustic panels contain large percentages of recycled material. Some fiberglass products include more than 40% recycled glass, while certain polyester panels use fibers made from recycled plastic bottles. Think about that. The water bottle tossed away today could eventually help create a professional recording studio tomorrow. Millions of discarded containers gain a second life as advanced acoustic products. Before manufacturing begins, every shipment undergoes strict inspection. Engineers measure moisture levels, particle sizes, chemical composition, and density. If raw materials fall outside specification, entire shipments can be rejected. A defect this early could affect thousands of finished panels later. That's why factories treat incoming materials almost like a high-tech laboratory treats sensitive scientific equipment. After inspection, raw materials move through an international network of rail lines, cargo ships, warehouses, and specialized transport systems. Some materials travel more than 10,000 kilometers before reaching the factory floor. By the time production starts, dozens of companies and hundreds of workers may have already contributed to a single acoustic panel. Yet, the most extraordinary transformation still hasn't happened. Because next, engineers will take ordinary rock, sand, and recycled materials and turn them into products capable of controlling sound itself. Now comes the moment that changes everything. Inside the factory, mountains of basalt rock enter massive melting furnaces that operate at temperatures between 1,450 degrees Celsius and 1,600 degrees Celsius, or roughly 2,640 degrees Fahrenheit to 2,912 degrees Fahrenheit. That's hotter than many volcanic lava flows. As the rock melts into a glowing orange liquid, the air shimmers with heat and the entire building hums with the sound of giant industrial fans. What happens next looks less like manufacturing and more like controlled alchemy. The molten material flows into high-speed spinning wheels rotating at up to 7,000 revolutions per minute. Centrifugal force stretches the liquid rock into microscopic fibers thinner than human hair. Powerful air jets blast across the spinning system at speeds exceeding 100 kilometers per hour, helping form a tangled web of fibers. The process happens in seconds, yet it creates the sound-absorbing heart of the acoustic panel. If the factory produces fiberglass panels, the process follows a similar path. Silica, sand, limestone, soda ash, and recycled glass melt at approximately 1,500 degrees Celsius, or 2,732 degrees Fahrenheit. The mixture flows through precision nozzles where thousands of glowing filaments emerge continuously. You can hear a constant rushing sound as the fibers form. The air smells faintly metallic, and every movement happens with astonishing precision because even tiny variations can affect acoustic performance. Next, automated spray systems apply specialized binding agents onto the airborne fibers. These binders help lock the material together into stable sheets. The spray nozzles operate under carefully controlled pressures, often ranging from 2 to 6 bar, ensuring uniform coverage. Most people never see this stage. Yet this invisible coating determines whether a panel maintains its structure for years or begins to break down prematurely. The fiber blanket then lands on a continuously moving conveyor belt. Some production lines move at speeds of 10 to 30 meters per minute, while giant rollers compress the material to exact densities. Engineers carefully control thickness because different applications require different sound absorption characteristics. A recording studio panel might differ significantly from one designed for an office or concert hall. Now the material enters a curing oven stretching dozens of meters long. Temperatures typically range from 180 degrees Celsius to 250 degrees Celsius, or 356 degrees Fahrenheit to 482 degrees Fahrenheit, depending on the binder formulation. Inside, heat permanently bonds the fibers together. Warm air rushes through the chamber, while massive fans circulate energy throughout the system. The smell changes dramatically as the binder cures and transforms into a durable internal structure. After curing, cooling tunnels gradually reduce the material temperature. Workers and sensors constantly monitor expansion and contraction because sudden temperature changes could introduce internal stress. Infrared cameras scan the boards in real time, while cooling fans generate a steady roar across the production floor. What happens next surprised even experienced engineers when they first saw it. Computer-controlled cutting systems now take over. High-speed blades and CNC-guided equipment slice the giant boards into precise dimensions with tolerances often tighter than plus or minus 1 millimeter. Some cutting lines process hundreds of panels every hour. The machines move so smoothly that large sheets seem to glide effortlessly through the factory, even though thousands of kilograms of material pass through each shift. For decorative acoustic panels, another transformation begins. Automated fabric wrapping stations stretch carefully selected textiles across the panel surface. Tension systems pull the fabric evenly, while workers inspect corners and edges by hand. You hear the rapid clicking of pneumatic tools operating at pressures around 90 psi. In just a few minutes, an industrial board begins to look like a premium architectural product. Some manufacturers add decorative patterns using CNC routers, laser cutters, or precision molding systems. Geometric grooves, wave designs, and custom architectural textures emerge across the surface. Beyond aesthetics, these patterns can influence how sound interacts with the panel. Think about this. Every curve and every groove may help control echoes that your ears would otherwise detect instantly. Finally, finished panels move on to automated packaging lines. Robotic arms stack products with incredible accuracy, while barcode systems track every unit. Protective wrapping shields the panels from moisture and damage during transport. By this point, materials that began as rock, sand, and recycled waste have become sophisticated sound control devices ready for studios, offices, theaters, and homes around the world. But manufacturing the panel is only half the story. A beautiful panel means nothing if it fails to absorb sound, warps over time, or misses critical safety standards. So before a single product leaves a factory, engineers unleash some of the most advanced testing technology in modern manufacturing. And that's where the real battle between perfection and failure begins. The journey isn't over when an acoustic panel leaves a production line. In many factories, the most expensive equipment sits inside the testing department. Here, engineers don't ask whether a panel looks good. They ask whether it can control sound with scientific precision. And the answer often determines whether thousands of panels ship to customers or head straight back for recycling. One of the most fascinating rooms in the entire facility is the reverberation chamber. These giant concrete rooms allow engineers to measure exactly how much sound a panel absorbs. Powerful speakers blast control frequencies ranging from deep bass tones around 125 Hz to sharp high frequencies exceeding 4,000 Hz. Sensitive microphones record every reflection. What looks like an empty room becomes a battlefield between sound waves and engineering. The results appear as a number called the noise reduction coefficient, or NRC. High-performant acoustic panels can achieve NRC ratings between 0.85 and 1.00, meaning they absorb up to 100% of the sound energy that strikes them under test conditions. Think about that. A product only a few centimeters thick can effectively eliminate sound reflections that would otherwise fill an entire room with echo. Laser measurement systems now take over. Precision scanners sweep across every panel surface, searching for defects invisible to the human eye. Some systems detect dimensional variations smaller than 0.5 millimeters. A tiny warp, a slight thickness inconsistency, or an imperfect edge could affect installation quality. Thousands of measurements occur in seconds without a single human touch. Then artificial intelligence joins the process. High-speed vision systems capture hundreds of images per minute, while machine learning software searches for discoloration, fabric flaws, surface contamination, and manufacturing defects. Modern systems can identify problems with accuracy levels exceeding 99%. Most people never realize that AI may inspect the acoustic panel hanging in their office long before any human sees it. Not every panel passes. Depending on product type and quality requirements, rejection rates typically range between 1 and 5%. Some fail dimensional checks. Others miss acoustic targets. A few show cosmetic flaws that customers might never notice. Yet manufacturers reject them anyway, because consistency matters when thousands of panels must perform identically. Fire testing introduces another challenge. Many commercial buildings require acoustic panels that meet strict international standards. Engineers expose samples to control flames and extreme heat to evaluate fire resistance. Some panels must self-extinguish, while others must limit flame spread according to rigorous certification requirements. Watching a product intentionally set on fire never stops feeling dramatic. Durability testing pushes panels even further. Specialized machines simulate years of use in a matter of days. Environmental chambers cycle temperatures from freezing conditions to intense heat, while humidity levels rise and fall repeatedly. The goal is simple: discover weaknesses before customers ever experience them. What happens next often reveals flaws that normal inspections miss completely. And this is where human skill still beats machines. Experienced inspectors run their hands across fabric surfaces, examine stitching, and study subtle visual details that algorithms sometimes overlook. After years on the job, some specialists can spot issues within seconds. Technology handles the heavy lifting, but human judgment still protects the final standard of quality. Before shipment, every approved product receives identification codes linking it to specific production batches, material lots, and testing records. Months or even years later, manufacturers can trace a panel back to the exact day it was made. Few products maintain such detailed histories. It's like giving every acoustic panel its own permanent passport. Only after surviving all these tests does a panel earn approval to leave the factory. Yet an even bigger story remains. These products now fill offices, airports, schools, theaters, and recording studios across the planet. The scale of that global industry and the surprising fact behind it are far larger than most people could ever imagine. By the time an acoustic panel reaches a wall, it has already completed a journey spanning mines, recycling centers, furnaces, laboratories, and factories. Yet the scale of this industry extends far beyond any single building. Every year, manufacturers around the world produce hundreds of millions of square meters of acoustic treatment products. If placed edge to edge, the panels produced annually could cover entire metropolitan areas. Most people never realize how much engineering goes into making modern spaces sound comfortable. The global acoustic panel market now generates well over $10 billion annually, and analysts expect that figure to continue rising throughout the next decade. Growing cities, open-plan offices, podcast studios, streaming facilities, schools, hospitals, and entertainment venues all need better sound control. Think about this. As the world becomes noisier, the demand for silence becomes more valuable. Few industries benefit from that trend more than acoustic manufacturing. Today, the largest producers include China, the United States, Germany, India, and Turkey. Together, these countries account for a substantial share of global manufacturing capacity. China leads through large-scale production, while Germany specializes in advanced engineering and premium architectural systems. Meanwhile, emerging markets continue expanding as new commercial buildings demand higher acoustic standards than ever before. The industry directly and indirectly supports hundreds of thousands of jobs worldwide. Miners extract raw materials. Engineers design products. Factory workers operate production lines. Logistics teams move materials across continents. Architects specify installations. Acoustic consultants solve sound problems inside buildings. Behind every finished panel stands an enormous network of human expertise. The history of acoustic treatment stretches back much further than many people expect. Early theaters and concert halls relied on heavy curtains, carved wood, and architectural geometry to manage sound. During the 20th century, advances in mineral fibers, fiberglass, and acoustic science transformed the industry. What once depended largely on trial and error evolved into a discipline driven by mathematics, physics, and precision engineering. Over the last 50 years, acoustic panels have changed dramatically. Early products often focused purely on performance. Modern systems combine sound absorption, fire safety, sustainability, durability, and architectural beauty. Some contemporary designs look more like artwork than industrial products. Yet beneath every elegant surface, the same mission remains: controlling sound before it becomes noise. And this is where the future gets truly extraordinary. Manufacturers are developing smart acoustic panels with embedded sensors capable of monitoring room conditions in real time. Researchers are experimenting with recycled biomaterials, advanced composites, and adaptive surfaces that can change acoustic behavior. What sounds futuristic today may become standard technology within the next 10 years. Did you know that some anechoic chambers built with specialized acoustic panels absorb so much sound that people can hear their own heartbeat? Did you know that poorly controlled office noise can significantly reduce productivity? And did you know that modern recording studios depend on acoustic treatments so effective that even tiny design changes can alter the way music sounds? These products influence daily life far more than most people realize. What began as volcanic rock, silica sand, recycled glass, and plastic waste has become a technology that quietly shapes how humans communicate, learn, work, and create. The greatest achievement of acoustic panels may be their invisibility. When they perform perfectly, most people never notice them at all. Yet without them, modern life would sound completely different. From the depths of quarries to blazing furnaces, from microscopic fibers to advanced AI inspection systems, you follow the complete journey of one of the most overlooked products in modern engineering. Every acoustic panel represents thousands of decisions, countless hours of work, and decades of scientific research. Most people see a decorative wall feature. You now see a precisely engineered device designed to control one of nature's most powerful forces: sound. The next time you walk into a recording studio, office, classroom, cinema, or concert hall, look around carefully. Hidden in plain sight, acoustic panels work silently every second, shaping every conversation, every performance, and every moment of concentration. They don't move. They don't make noise. Yet they transform entire environments in ways that few technologies can match. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.